Excellent. All right, the first talk in today's session will be Value Iteration Networks on Multiple Levels of Abstraction by Daniel Schleich, Tobias Klamt, and Sven Beckner. And Daniel will be presenting.
Good morning. I'm Daniel Schleich from the University of Bonn, and I'm going to present you our work on value iteration networks of multiple levels of abstraction. Traditional planning approaches, like search and sampling-based approaches, tend to do extensive iterative searches, which results in long planning times for complex domains. Learning-based planners are promising since they have an increased scene understanding and thus may speed up the planning process. One example are value iteration networks, short VINs by Tamar et al., which learn goal-directed behavior and generalization to unseen domains. Input to the system is an environment map as well as a one-hot goal map. These are processed by a neural network, which approximates the value iteration algorithm and finally maps the resulting state values to probabilities over the next possible actions. VINs have shown promising results on small and low-dimensional domains. However, it's difficult to apply them to most real-world problems, since the number of necessary value iterations, and thus also the hardware requirements, significantly increase for larger state spaces. We reduce the state space size by introducing multiple levels of abstraction to the whole architecture. On the first level, we only represent the vicinity of the robot, but at full resolution. For level 2, the resolution is half, but the number of map cells is kept constant, thus it covers a 4 times larger region. This step is repeated to obtain level 3, resulting in a map at 1/4 of the original resolution and an area which is 16 times larger than the level 1 area. Reducing the resolution on the higher levels results in information loss, which we compensate by adding additional descriptive features for each abstract map cell. We combine this representation with value iteration networks. In a first step, we let the network learn the abstract environment representations. We then extend value iteration networks to perform value iteration on each of these representation levels in parallel with enabled information flow after each value iteration for the different levels. The whole formulation is fully differentiable and thus allows end-to-end training using backpropagation. We evaluated our approach on 2D grid worlds with sizes up to 128 cells in each dimension. These maps were very challenging for VINs. Hierarchical VINs, also by Tamar et al., are able to improve the performance by using multi-resolutional representations in coarse-to-fine planning without additional descriptive features. Our approach outperforms both VINs and H-VINs with respect to result quality while significantly reducing the memory consumption. Furthermore, we investigated whether we can apply our approach to solve significantly more complex planning tasks, such as 3D locomotion planning, and we successfully integrated it into a planning pipeline for the Centauro robot. The footprint of the robot was fixed during the experiments, but as you can see here, the robot had to take obstacles between its legs. On average, we achieve a success rate of roughly 75%, while the obtained paths are optimal or near to optimal with similar planning times than an I-style planner. So to summarize, we extend value iteration networks to employ multiple levels of abstraction, where the coarser resolution of higher abstraction levels is compensated with additional descriptive features. Thus, we increase the result quality while reducing the memory consumption and are able to extend the applicability to larger state spaces. Thank you for your attention.
And we will have time for all questions at the end of the session. But now I'd like to introduce the second talk, Autonomous Tool Construction Using Part Shape and Attachment Prediction by Lakshmi Valyandar Nair, Nitin Srikanth, Zachary Erickson, and Sonia Trinova. And Sonia Trinova will be presenting.
Hi, I'm Sonia Trinova. I'll be talking about my students' work. Lakshmi Nair couldn't make it today for visa issues. My team and I are from Georgia Tech, and I'll be talking about autonomous tool construction. So today, when we deploy our robotic systems, we generally assume that they have the tools needed to perform their function, or maybe that substitutes could be found in the environment. But in some applications, like remote exploration, tools and their substitutes might not be available. And in such cases, the ability to actually construct tools out of pieces in the environment can greatly increase a robot's adaptability. So we contribute a novel approach for tool construction, where given a reference action, such as let's hit something, and a set of parts from the environment, our approach outputs a ranking of which parts can be combined and how in order to produce a tool that meets the needs for the required action. And so then the robot physically constructs the tool and validates it in the physical world. In comparison to prior work in this area, our novel approach is more computationally efficient and incorporates more advanced forms of reasoning about shape as well as attachments of different parts. Our work is also novel in its use of material properties through spectroscopy to analyze which objects could be attached together. Combined, what these contributions mean is that we're able to construct more diverse tools than we could before. The way we do this is through two scoring functions. The first considers shape and similarity of the thing we're constructing to typical tools used to perform that action. So we're given an action such as hit, we automatically extract hitting tools from the tool web dataset and then use a set of neural networks to rank and compare and score the similarity of shape between those tools and what we're constructing. Our other scoring function is attachment scoring. Given two parts in a relative configuration, we assess whether they could be joined together to produce the shape we want. And we're considering three different types of attachments: grasping, magnetic, and pierce attachments when one object pierces another. For each of these attachment types, we have a numerical function that is able to predict whether two parts that we see on the table are likely to be joined using that attachment. And again, this is probably the widest range of attachment that's been considered in prior work. What you're seeing in the video is the robot reasoning about pierceability attachments. It's using a handheld spectroscopy sensor to predict whether the part is pierceable by something narrow and sharp. This is an extension of material classification work, also based on spectroscopy, that was presented at ICRA last month. Given all this data, the ultimate outcome is a ranking of parts that can be combined to build tools using a weighted sum of shape and attachment data. Using that ranked list, the robot iteratively constructs tools and validates them to see which one works, and stops once it reaches a tool that works. We have considered 5 different action types, and our results indicate that this form of reasoning that combines shape and attachment data outperforms attachment-only and shape-only reasoning that's been used in the past, as well as other baselines. And what this ultimately means is that our approach takes on average only 2 tries to combine the pieces in the right way to create a functional tool, given a dozen potential configurations that are possible. And so here's a video of several tools being constructed: a spatula, a scoop, a squeegee, and a hammer. Remember, the robot has no prior knowledge of what's in front of it. It's using only point cloud data and spectroscopy data to do this, though we are providing the trajectories needed for the attachments and the tool trials in this particular case. And depending what we put in front of the robot on the table, different tools are constructed to achieve similar goals. You can see the diversity shown here. Thank you for your time.
The next presentation is entitled Learning to Walk via Deep Reinforcement Learning by Thomas Harnoy, Sehun Ha, Ulrich Zhao, Jay Tan, George Tucker, and Sergey Levin, and Thomas Harnoy will be presenting.
Hello everyone, my name is Thomas Harnoy. I will describe a work we did in collaboration between Google Brain and UC Berkeley. In this project, we demonstrate that we can learn quadrupedal locomotion using deep reinforcement learning directly on the real robot without relying on simulation or models. Many real-world domains are diverse and complex, and modeling them accurately can be prohibitively challenging. Moreover, an agent should be able to adapt to changes in the dynamics to the wear and tear, and to any new situations it may encounter after being deployed. A promising approach is to learn behaviors from data. A learned behavior can in principle handle anything that is present in the data, And moreover, the agent can keep improving itself after it has been deployed. Unfortunately, learning behaviors can require a lot of data, and collecting real data on the real system can be really expensive. Therefore, many prior works focus on minimizing the cost of data collection. For example, one can collect data from multiple robots running in parallel and automate the environment resets to enable data collection around the clock. Unfortunately, these approaches set additional constraints to the task and shifts the focus from learning to designing the task itself. Instead, we consider an off-the-shelf quadruped that requires manual intervention during training all the time, and training cannot thus be easily automated. Therefore, we focus on the root cause, namely poor sample complexity, and specifically, we aim to minimize the cost of tuning hyperparameters. Our starting point is the maximum entropy objective shown here, which maximizes both the return and the entropy. This objective couples exploration and exploitation corresponding to the two terms, and it has been previously shown to lead to algorithms that are sample efficient and robust. Unfortunately, it also introduces a new hyperparameter, the temperature, that controls the trade-off between the two terms. Tuning the temperature is really important and it needs to be done independently for each task at hand. To overcome that issue, we set up a new objective where we optimize or maximize only the return, subject to a constraint on the expected entropy. We still need to use the target entropy, but we found that to be a substantially easier problem than choosing the temperature. In this new formulation, the temperature takes the role of the dual variable, and we can optimize it using dual gradient descent. Our implementation is based on soft actor gradient, and our work extends SAC with learned temperature. We first benchmarked our algorithm in simulation, shown here in blue, against soft actor gradient with a fixed temperature, as well as other popular reinforcement learning algorithms. As you can see, our algorithm can match and sometimes outperform the other algorithms, even though our algorithm doesn't require any environment-specific tuning, and we ran all these experiments with a single set of parameters. We also used our algorithm to train a quadruped to walk. Here you see the agent initially takes random actions. Over time, the policy improves, and the agent starts preferring actions that lead forward moves. Overall, training took about 2 hours, which amounts to about 400 episodes. Even though the training was fully done on flat terrain, we later tested the converged policy on different kinds of terrains, and it can robustly handle all these unseen situations. We believe that the reason for good robustness is that maximum entry policies that visit wider range of states, diversifying the data, and also because we train only in the real world, the data is more diverse due to natural perturbations, and therefore the agent can handle these unexpected situations better. Thank you.
The next talk is entitled Simultaneously Learning Vision and Feature-Based Control Policies for a Real-World Ball and Cup, and the authors are Devin Schwab, Joost Tobias Springenberg, Murilo Fernandez Martins, Michael Nunert, Thomas Lamp, Abbas Abdulhamati, Tim Hartwick, Roland Hafner, Francesco Nori, and Martin Riedmiller.
Hello, my name is Devin Schwab. I'm going to be presenting our work, Simultaneously Learning Vision and Feature-Based Control Policies for Real-World Ball and a Cup. And you can see all the other authors that worked on this paper here. Our motivation is that we want to learn robot control policies from high-dimensional sensor data, such as cameras. We specifically focus on vision policies. There are many approaches to this, but we wanted to work on something that would reduce the amount of training time and data required, as well as be able to train and execute directly on a real robot. So our goal is to scale up robot learning of control policies with high-dimensional sensors, and our approach is based on using auxiliary tasks that differ in both rewards and state spaces. Our approach is based on the Schedule Auxiliary Control Framework, or SACX for short, which at a high level speeds up training by executing and learning multiple auxiliary tasks that differ by reward. The data from each task while executing during training is used to update all the other tasks, and so you get a speed up from the synergy between the different tasks. And our extension allows the tasks to differ not only by the reward, but also by the state space, which allows us to create some tasks that have a low-dimensional feature state space for the task, with the assumption being that control policies from the low-dimensional features will converge faster than control policies using the high-dimensional features. These feature-based policies learn faster and therefore generate useful training data for the vision-based policies, which speed things up. And then at test time, we can ignore the feature-based policies and rely only on the vision-based policies that were our ultimate goal. This is a high-level overview of our network architecture. We use an actor-critic method. We start by splitting the state observations into different subsets. You can see a vision subset, a feature subset, and a common subset, which includes things like proprioceptive features. These are each passed through their own individual G neural networks, which are learned sort of as a pre-processing step. We then have task-specific indicators, which enable or disable the outputs of these G networks. All of the outputs of these are then passed into a common learned F network, which outputs the final values of our network. In the actor's case, we are controlling joint velocities using a Gaussian policy, where our network outputs means and diagonals of a covariance matrix. The critic uses a very similar structure. So essentially it would be this, but with the output being Q values. Here you can see an image of what our real robot setup looks like. We tested all of this on the ball in a cup tasks. You can see the robot arm holding a cup, with the goal being that we're going to swing that ball up as quickly as possible and catch it in the cup. For the feature-based states, we use a motion capture system. You can see the cameras attached to the frame surrounding it. And here is an example of our simulation. We did a number of experiments to test how fast our approach was compared to existing methods. And here we can see the robot executing the final policy learned in the real world. This was learned directly on the robot. On the left, you can see what the vision inputs look like for the robot. You can see they're quite pixelated. We didn't do any sort of vision corrections, so nothing to deal with motion blur, lensing, color correction. And the images are quite low resolution. We also tested to see how robust the policies were. Was it actually closed loop, or was it just memorizing a trajectory? And as you can see, it actually is adjusting to the states. We did some experiments where we also blocked cameras to see that it actually was using the vision information. In conclusion, our approach of learning with both feature-based and vision-based auxiliary tasks significantly speeded up training. In simulation, our approach was about 8 times faster than learning with only vision-based auxiliary tasks. And our approach works on real robots and dynamic tasks. We were able to train the vision-based policies from scratch on a single real robot for the ball in a cup task. Thank you.
All right, and the last talk in this morning's session is called Let's Drive, Driving Among a Crowd by Learning from Tree Search by Panpan Kai, Yuanfu Lo, Asim Saxena, David Su, and Wei-Sun Lee.
Good morning. My name is Panpan Tai. I'm presenting Let's Drive, Driving the Crowd by Learning from Tree Search. And this is a collaborative work from the National University of Singapore. Driving a dense crowd is an unsolved challenge for autonomous vehicles. The vehicle have to interact with many other agents who intensively interact with each other. Failing to plan in such an environment can get the robot stuck in the crowd or lead to accidents. So the main difficulty in this problem is partial observability. The vehicle only have noisy observations of surrounding agents. And this essentially lifts the problem up to the space of beliefs that are probability distributions over hidden states. And in this case, hidden states are intentions of other pedestrians. And importantly, the planning here have to be conducted on a high-dimensional belief space. State-of-the-art approaches take 2 ways. One can either learn a policy from expert demonstrations or through reinforcement learning. That's like how we gather our daily experience. Or one can perform planning, executing belief tree search to compute a policy for the current situation. And this is like how we solve problems on the fly. But for really complex problems, like driving among a dense crowd, neither of these 2 approaches can work well alone because of insufficient data for learning and limited time for planning. In our approach, Let's Drive integrates planning and learning to leverage and advance the capability of both. We have an offline imitation stage to acquire driving experience and an online improvement stage to search for the optimal steering angles and accelerations. So in the imitation stage, we first execute imitation learning using a belief tree search expert to train a policy network and a value network. Then in the improvement stage, we again execute belief tree search in real time to drive the vehicle. Now this belief tree search is guided by the neural networks we just trained. We use the policy network to bias action selections, and we use value network to represent value estimations of unsearched subtrees. Essentially, this is using the neural networks as prior knowledge, and we are conducting additional search upon this prior knowledge to further optimize for a particular problem instance. The architecture of the policy network is designed according to our domain knowledge in planning. We first develop an initial plan using a gated path planning network. Then the plan is refined using a CNN with residual connections to produce the policy and the value. Now, the scheme of Let's Drive is inspired by the AlphaGo, while the driving problem here is much more complex than the Go game, with only 2 players and perfect board information. Here, the vehicle have to interact with many other agents. All of them are partially observable and conducting highly uncertain motion. And we trained our neural networks on a set of training maps with randomly generated crowds. And results show that, first of all, the neural networks learns properly from the training expert, able to achieve similar driving performance through imitation learning. And by further combining planning with learning, Let's Drive significantly outperforms either boundary planning or imitation learning alone, achieving the lowest collision rate, highest efficiency, and best smoothness given the same planning time. And this approach also generalizes well to unseen maps, also outperforming both boundary planning and imitation learning alone. So now these are a bunch of driving examples on different maps. The vehicle is executing Let's Drive in real time. It is able to make its way efficiently through dense crowds in different environments through tricky maneuvering skills. And welcome to discuss with us as the poster section. Thanks.
All right, I would now invite all of the speakers in this session to come up to the stage for Q&A. So we'll have about 10 minutes for questions. Please raise your hand, and one of the volunteers will bring you a very nice throwable microphone. Okay, well, maybe I'll start. Oh, is there a question there? Okay, maybe I'll start off with a question. So this is a question for Devin Schwab about the Ball and Cup game. So one of the things about the Ball and Cup is that a lot of prior work has also studied this task, oftentimes with open loop policies. Could you say a few words about what you think the kind of the closed loop vision-based control is doing differently from the open loop policies?
Sure. Sorry. So I think that the closed loop does a good job, as you saw when we interact with it. It actually, I mean, if you mess with the ball, it just keeps going at it until it eventually gets it in the cup. And I think that while that's interesting in this task, it shows that this approach is useful for, I mean, non-toy examples where you really want the robot to keep trying and going at it rather than just memorizing an open loop control. And also our approach from the previous work that used these open loop trajectories is significantly different in terms of the fact that we end up being able to use these high dimensional sensors instead of, like there was work from Jan Peters that used a lot of task specific features, which we use in the training step, but at test time we no longer need that information. So I think just as the approaches are very different compared to the previous work.
All right, thank you. Any other questions from the audience? There's a question over here. So if you ask a question, you should be good at catching.
Okay. I think it was the first speaker to have the question. So why did you need to compensate for decreased resolution, for high abstraction maps with more features? And did you really need it? Did you try without? Was it very bad?
So we had the comparison between the hierarchical VINs, which exactly do this, so they have no additional features, but multi-resolution. And yeah, as you could see, we achieve higher success rates, so it was necessary. And we did some additional experiments with maze worlds, which I couldn't show due to the time, but there we significantly outperform the hierarchical approach. Yeah, so it's necessary.
I have a question to the final speaker of that session. So there has been a lot of work about robots, like navigating in crowds, and so there's a lot of work in collision avoidance. So if you consider this as a drive if you can scenario, right? So how much better is your approach than just the collision avoidance that tries to follow a path and stops when there's something?
Yeah. So actually, we did compare to collision avoidance algorithms like Orca-based algorithms and the planning-based algorithms. So the results show that we significantly outperforms any of these approaches like collision avoidance, planning, and learning alone. But essentially, what is the difference is that we do long-term planning in a belief space. So we think about both exploitation and exploration, and we look ahead for really long.
Does anyone else have any questions? There's a question in the back.
This is for the mini tower walking speaker. I was wondering if you could talk first a little bit about maybe the limitations of how far your learning was able to get in terms of what kind of inclines could you handle, and then also how would you address the challenges of perhaps different surfaces, for instance, like walking on sand if you don't have the option to intervene during that learning process.
Okay, so our framework was really limited. We didn't have any sensors on the legs and so on, so we did not test on how well it can generalize to like really arbitrary scenarios. So in practice, it would make sense to include all the sensory information from the legs as well and have a little bit more variation on the terrains and then testing more on various other scenarios, I think would make more sense. So this test was mainly meant to prove that we can actually train on the real platform, and that way we can optimize directly on the system that we care for.
Thank you.
Any other questions? There's a question in the front here.
This is for the Let's Drive, the paper. Can you maybe explain what is being learned and what is being pre-programmed in the algorithm?
So the learned thing is basically a policy that is learned from your driving experience and its corresponding value function. And what has been programmed or what has been planned is to simulate the uncertain future, and you optimize the vehicle's steering angles and accelerations at runtime. So, and these two things are integrated together by injecting the neural networks into heuristics of the search.
Yeah.
There's a question over there.
Hi, Arnoya. Hi. I just wanted to ask you a question regarding your work, actually. So did you try to compare your algorithms, for example, with previous work in RL as well, like policy modulated trunk trajectories, or even with open loop? And if there anything that you can comment about that?
We did not compare on the real system to other algorithms. Only in simulation we show that we can actually outperform other reinforcement learning algorithms that don't use any prior works and prior knowledge.
There's a question in the front.
So I have a question to this, again, another one, but this time to the cool tool construction robot. So how far are you actually away from building tools that can also be used?
So that's a really great question. The second part of the problem that we haven't addressed yet is how do you actually then go through the trajectory process of actually using the thing you've constructed, which can have different dimensions than a typical tool. Teska Fitzgerald has been working on that for her PhD, for those who know her. But we haven't combined the two works, and so the goal is then kind of next step is to do that. So I think there's still a little bit of work to do on not just building, but also then using the tool and transferring tasks from other tools that you know.
Any other questions? Okay, well, if there are no other questions, then we will, there's a question up here.
I want to have a question about the second speaker. So that's really interesting work to working with let a robot use a tool. So I'm wondering, for your tool, you connect two parts together, and do you also consider about how you can combine your tool with robot together as like a kind of extension for the body schema?
I think that's a great question. So we can theoretically combine more than two parts, and also you can think about the robot as a part of a tool. So I don't have any videos of that in action, but I think that the underlying framework would support that kind of work.
Okay, thanks.
All right, well, that concludes the first morning session. Let's thank all of the speakers one more time. And hand it off to the next session chair.